Let's welcome Dr. Liu.
Well, thank you so much for the introduction. I'm a native Cantonese, so I would like to say hello in my native tongue. 大家好. Before we start, I want to make a statement first. The previous speaker said Zhejiang would be the Silicon Valley of China. No, it's right here. It's centered around SS. It's right here in Hong Kong. So before we introduce the talk here, I want to make an introduction, acknowledge one of our strong collaborators, Yiming. Please stand up. So a lot of work here is a collaboration between the two institutes. Thank you. So let's get started. Today I want to talk about Embodied AI, particularly open source computing stack for Embodied AI. So I will start by introducing what we think as Embodied AI and why we do open sourcing, and some of the work that's been going on. So I think it's one word to capture the essence of Embodied AI. It's scalability. So we wrote 2 articles on communications of ACN to introduce the concept. But if we look at using financial terms to look at these 2 diagrams, quite interesting. We listed 4 companies, 2 autonomous driving company, Aurora, Too Simple, and then 2 internet companies, Alphabet and Microsoft. If you look at how much money they spend on R&D, you look at Aurora, Too Simple, it's almost 80%. That's not healthy financially if you spend 80% on R&D. And if you look at Alphabet and Microsoft, they spend about 20%, which is a very healthy development. Oops. Then you ask the next question, how much money can each employee generate for these companies? For Aurora, Too Simple, it's almost 0. But then for Alphabet and Microsoft, it's a tremendous amount of money they generate for each employee, about $2 million per year. Why? Because internet companies, their business model is scalable, whereas robotic companies, before Embodied AI, they're not scalable. What do I mean by that? You spend a lot of money and research efforts onto one product that does not sell very well. Everything is specialized. But Embodied AI, the reason that Embodied AI brings scalability, because you develop one stack, one software stack enables various forms of robots. And then once we hit that, we will see companies going into the scale of Alphabet and Microsoft. Especially with that kind of scalability, you are really facing a business that makes a lot of money. So that's Embodied AI, but why open source, right? We want to list a few examples. First is NASA. Within NASA, there's a core flight system. This system is sharing the code within NASA so that each NASA launch project can save about $4 million. So internal sharing already brings a lot of benefits. The second example is what we do at the very beginning of the industry. For example, ROS. Everybody in here, I think, knows about ROS, Robot Operating System. They started very early. About 10, 15 years ago, they started this project, while not many people were doing research. But gradually, as the field advanced, they became the standard for all the robotic work. The final example, Linux. I think everybody is very familiar with Linux. I think now Linux is already a fundamental infrastructure of the world. So where is Embodied AI? It's right between ROS and Linux. If you do it well, you can dominate the next age of computing. So that's why we started as an open source project. The first piece of open sourcing, it's called Airship that we developed at AIRS, Shenzhen Institute of Artificial Intelligence and Robotics. Basically, it's a modular design such that you have the traditional navigation, you have the traditional grasping. What's the key is the LLM that can sort of dissect the user's intention, and then we design a task schedule to dispatch the intention into individual units to execute. That turns out to be the most useful design for companies that are already in the field of robotics, such as cleaning robots and so on and so forth. So that's our hardware architecture for Airship. It's also modular design. You see a very small chassis with an arm on top of it, but that's the form factor with the biggest demand today. In terms of sensors, we have the traditional stuff, LiDAR, IMU, camera, eye-in-hand camera as well. Then you have computing unit, motion controller, standard design, and we open source that as well. So I was working at Microsoft after I graduated. So the first phrase I learned from the team was that you are as good as your tools. So you need the best tools to facilitate your software development. So under Airship, we also open source a simulation platform built on top of NVIDIA ISAC so that people can develop on the platform, test it in the platform before they deploy the project to the field. So how is it doing today? We show a few examples. On this side, that shows a collaboration between us and Yiming in the Chinese Academy of Sciences. That's a fairly high-end robot, very agile hands that can carry out a lot of different functions. And then we deploy it as a service robot and perform quite well. On the left side, it's a startup company within Shenzhen enabled by our Airship project. It's a retail robot, such that they can open the door and open the door of the machine to get, for example, medicine for the customers. This one is going to sell big. It's a cleaning robot. China is already shipping about 10 million units of cleaning robot each year. The next frontier of that is the robot wants to grab stuff from the ground so that it can keep cleaning. Each time you get rid of a barrier like that, your market share will increase by about a fold, 100%. On the lower right-hand side, you see a mowing robot to cut grasses, but then they are facing the same problems. As you have objects on the ground, the robot can pick it up and then drop it. So these are the common applications for Airship, and it's being commercialized. But today's main talk is about Airstone. When we talk to entrepreneurs or industry people in the field, their feedback is that it's great to have a software stack, but the main problem they're facing, can you ship it on a chip that's within $50 US instead of an NVIDIA chip that's thousands of dollars? Can you ship it within 50? That's the key milestone we try to accomplish. So we divide it into 3 different milestones. First one is how do you do the accelerator design? And then through the Airstone project, we kind of open source all the basic accelerator design, including localization, planning, control, and so on and so forth. Oops. Milestone 2, it's EDA, but when we say EDA, it has quite a different connotation compared to traditional EDA. We'll explain. The third is the full stack compute system. How do we do a full system that can run on a chip that's within $50? So we have open sourced some of the projects, and Yiming contributed a lot to this work. But basically, planning and control, it's a basic form for robotic computing. Then we think that those basic operators are still valid, and we will still use the basic operators for years to come before we hit end-to-end architecture. We will discuss later. And then the second piece of work is EDA. Here it shows an example. You have a simulation, but it's hardware in the loop, meaning that the compute is connected to the simulator. The simulator feeds image to the compute unit. The compute unit then will derive the instruction for the car. Then if you inject faults into the simulator, you can actually see a crash. Then you can, based on that, develop architectures to be more robust. So that's what we mean by EDA. Traditionally, EDA is just help you to design the chip, but I think we expand the scope of EDA to make it more well-rounded, such that it can simulate the environment as well. I do think that's a very key step for robotic chip design. Another collaboration with Yiming, I think when humans think, they have a fast system and a slow system. Today, when we deploy embodied AI or autonomous driving, it's all a slow system. So the whole pipeline becomes very slow. But if you can use 90% of the time use a fast system, and then 10% of the time using a slow system, it becomes much more efficient. So Yiming is going to present this work at ESCA 25 in Tokyo next month. Benchmarking, that's our current work. So for a field, when we want to study something, we need to develop benchmark. But what we see today is the benchmark's missing. Most of the benchmark we see is just one ROS node focusing on one application. I don't think that's enough, given that the enormous amount of application we see today. So here's the breakdown of the benchmark. You have ChatGPT, you have QN, you have Llama, VLA. That's for the LLM side. For object detection side, you have something else. For molecular camera side, you have something else. So it's a big suite of benchmarks that you can combine together to facilitate different kind of applications. And that's our current work. Finally, some thoughts for embodied AI architecture. First one is modular design, but a lot of people criticize modular design, saying that, oh, that's not the future. But we do think from commercial side, what we see is that for the next 5 to 10 years, modular design will still dominate. The breakdown would be you have a data flow kind of architecture at the below to control all the basic operators. That would take about 20% of your compute power. But 80% of the compute power would be going into your large language module because that's your application. What's different from a medical robot compared to, say, a cleaning robot? It's your LLM. So we want to reserve most of the compute power for the LLM, 20% for the basic design. Design two is called decoupled models. So we think there would be one decision model and a control model. That's it, because you can take decision model, and then you can put it on a four-legged robot control model, then you have your system built. Or you can take the decision model, put it on a humanoid robot, then you have a system built. The question becomes, how do you do the decision model, and how do you do the control model? We, at the AIRS Research Lab, we are doing active research on this field, hopefully to update everyone with some good news later. But I do believe this is the future. Decouple model, because that enables another level of scalability. You can use one decision model to put it into different control models, and vice versa. Now, the last one is a very hot topic. I think some previous speaker touched upon VLA. But VLA is very good if you have only one form factor. You just train the hell out of that one form factor, that would work. But if you change the form factor, you have to retrain the whole model chain. I don't think that's a scalable approach. So to me, I think the decouple model would be the